impacts of a sizable nature are pretty infrequent. Past that, we have another series of planets, Jupiter, Saturn, Uranus, and Neptune, that are completely different. They're not high temperature, rocky type planets with metallic cores. These guys are essentially frozen gases. We're getting further away from the sun. The solar system's getting colder out there. Gases that are in vapor stage here are in frozen solid stage out there. And you can see they've become giant planets. Jupiter rules the world, essentially. It has a gravitational field that basically just dictates what happens in that part of the solar system. And here at the very end, little old Pluto, are now what we call a dwarf planet, is more like what we call the Kuiper Belt and Oort cloud bodies that are out here, and this is where comets come from. And these are the remnants that haven't been accreted to make the 4 giant frozen planets. So we've got some order to the universe, and all of them sit in that plane that cuts through the equator of the sun, and that's the original nebula plane that was rotating around the proto-sun, and that kind of dictates the shape of our solar system. I would remember the planets in order furthest from the sun to nearest to the sun. It tends to show up on exams quite a bit, so there's a safety hint for your notes. So, where are we now? Well, here's our Orpheus-Earth collision, and there's our closed system of today, but it only gets us back 4.5 billion years ago on Earth. The rest of the Big Bang, the bang back to 13.8 billion years ago, we have to look other places. We have to map other parts of the universe to see that, where it wasn't destroyed or grossly changed by this collision. Can we get back beyond 13.8 billion years? It's a closed system till then, but then it's an open system again, and maybe we can get back beyond that, but it might mean we go into a parallel universe or another scale. We have to get further away from what happened locally to get into that closed system. So maybe someday we can get far enough away and see deep enough into space. Okay, so I've got this new Earth that's molten. It's going to take about 100,000 years for it to start cooling down again. So I've just got this molten blob of rock material out there. I have no ocean, I have no atmosphere, that'll get blown away. So finally, we have to start cooling Earth down and rebuilding our ocean, rebuilding our atmosphere, assuming we had one to begin with. How am I going to do that? Where's this going to come from? Well, we think it's a process that we see going on today that actually makes Earth fairly unique. It took about 5 billion years because we really don't see a well-defined atmosphere and possibly an ocean until about 4 billion years ago. So it took from the Orpheus-Earth collision of about 4.5, 4.4, someplace in there, to 4.0 billion years ago before we see the beginnings of an atmosphere. And it wasn't an atmosphere like we have today. Where we think these gases came from was from within the planet. This accretion process did a couple things. Any atmosphere that might have existed before, bits and pieces of those gases got trapped in the clumping together and building of these planets, the accretion phase. So a lot of gas was trapped inside the planet, and that gas is trying to escape and get out. We see that today in the form of volcanoes.
question?
I'm just curious, is that a theory that geologists have, is that collision is what made Earth like exceptional, like the ability to host life?
No. No. We're going to talk about that some more, though. But what made life possible was just the ability to do photosynthesis. If we look at oxygen in the atmosphere, it did not come from this outgassing process. So we could not have been begun or survived in the early atmosphere that we see starting at 4.0 billion years ago. That was primarily an atmosphere of methane, CO2, water vapor, a few other little obnoxious gases, but no oxygen. So there's no way we would have shown up at the beginnings of this part of Earth's history.
Wouldn't the till be necessary for life, though?
Well, the tilt is important because it keeps the weather patterns in place. And the moon also helps stabilize that tilt and keep it from going. If Earth just tumbled, I mean, you wouldn't have seasons. You just have this random, well, 1 minute it's freezing cold, the next is burning hot. It just depends on your orientation to the equator as you tumble through space. But with rotation around a pole that is, in a large sense, fixed by having the moon out there keeping it in position, that means that Earth now has bands of weather so that you can plan on, well, it's going to be spring, I better get the wheat in, and I can harvest it in fall, and next spring I better get the wheat in again. You can grow crops, you can raise animals, and you have some seasonality that gives you a way of basically supporting yourself. If it weren't for those things, we wouldn't be here. If you look at the growth of populations around the world, populations easily spread east and west because the weather's the same there. The belts of weather are kind of the same east and west. But if you go north and south, it's much more difficult. I mean, for instance, if I went north from here and I went up to northern Canada, boy, that'd be pretty nasty weather up there, wouldn't it? Or if I went south, I'd be near the equator. It would be a whole different crop of plants and animals and things that I could grow there. So moving north and south is tough. Moving east and west is easy. So just those weather patterns really dictate the way life can move and spread around Earth. But this process, outgassing, we're getting those gases out of the planet, and now they can accumulate as an atmosphere around the planet. And we have water vapor, nitrogen, a lot of nitrogen. And nitrogen hangs around because it's a fairly heavy element. It's hard to let it escape out into space, and it doesn't react much with things. So it's one of those things that just kind of accumulates and hangs around in our atmosphere. Our atmosphere is basically 79% nitrogen. It doesn't do a whole lot for us, but it gives us some gas to move around. But if we look at volcanoes today, which are essentially outgassing, right? The ash coming out is rock particle material, but it's the gas that's driving it out. And when we look at present-day volcanoes, we see carbon monoxide, nitrogen, hydrogen, helium. We see a lot of chloride, sulfide, sulfur dioxide, a lot of water vapor, but no free oxygen. No plain old O2. What oxygen we see is all tied up already in water vapor. So where's the oxygen coming from to build our atmosphere so that we can survive? It's a waste product, yeah. We are the result of waste. If it weren't for the fact that something preceded us to do photosynthesis, which uses water vapor, carbon dioxide, to make organic compounds, sugars, amino acids, and the waste product that photosynthesis generates is O2, oxygen. So that means with oxygen starting to accumulate in the atmosphere, respiration can happen. And now the stage is set for us to begin. We can come along. And if we look at it, right after that Orpheus-Earth collision about 4.5 billion years ago, we've got a water, carbon dioxide, methane, ammonia, nitrogen atmosphere. We're not going to survive in that, let alone get started. And what you see is the water and carbon dioxide are going to start decreasing and disappearing. And at about 2.5 billion years ago, just 2 billion years worth of time, we start to see oxygen accumulate in the atmosphere. And we know that for a couple of reasons. But what's happening is this water and carbon dioxide are getting used up by photosynthesis, and oxygen is finally starting to be plentiful enough and accumulate and stick around in the atmosphere. So life was going on through this period of time, but it was life that did photosynthesis. And what we see, we have a rock that we've found, and that rock has been age dated, absolute age dated, at 3.5 billion years ago. And in that rock is this carbon film, which is drawn here to make it look a little plainer, and it is a bacteria. And bacteria are still with us, and they still do photosynthesis. So what they give off as waste product is what we take in as fuel, and the waste product, the CO2 that we give off, is what they take in as fuel. So it's a real symbiotic relationship. We're dependent on each other. And remember this idea when we built the periodic table, that we started with simple stuff and it got more and more and more complex? Well, the same thing's going on with life. We're starting out with single-celled, simple bacteria that do photosynthesis, about as simple as it gets. And that developed into multi-cell organisms. It started giving off oxygen. The state of the atmosphere changed and allowed other niches to be filled, other habitats to form. And now all of a sudden we can start over time filling those niches with a greater diversity of organisms. And that's what's gone on. Complexity has continued. But it still begs the question, where did this darn bacteria come from? And somewhere along the line, life had to begin. It didn't begin as us, but we've got to somehow start making a bacteria. So how do we do that? And that's what science is working on. What are the steps to take inorganic material, take the basic elements, combine them in such a way that we're starting to make organic elements, and somehow those organic elements start a series of chemical reactions that basically can be defined as the beginnings of life. And we're partway there. Back in the 50s, there were a couple of key experiments that used the early atmosphere of Earth and put a spark through it, and lo and behold, it produced amino acids. So we took inorganic material and we made organic materials. We made the building blocks of life. Now, we have made a couple more steps, but we still haven't figured out all the steps to make it happen. Now, remember our discussion about science versus religion? Notice here that this is just science. I haven't addressed the question of where does God fit in, how did life begin, how did God do this? All we're looking at is what are the steps necessary to take inorganic material, make organic material, and get that started in some kind of a sustainable chemical reaction type of system, life. We're just looking at what are the steps. We're not trying to answer who, we're not trying to answer is there a God. We're simply trying to figure out what are the necessary steps to make this all happen. And we think those are knowable steps. They fit the laws of chemistry, biology, physics. We'll figure it out. And geology adds its bit of evidence to show that it really happened. So I think during your lifetimes, the chances of actually figuring out how to start life might be answered. I don't think that's going to do anything to resolve the religious part of it, but it's sure going to be interesting from the scientific viewpoint. I think you guys can see some big revolutions in the way we think about things.
Hoverboards.
What's that?
When do we get hoverboards?
yeah. It's going to be cool. There is so much going on in the space exploration now. I think we're going to see things on other planets that give us a whole nother perspective of our solar system. We're finding other solar systems out there that look like our solar system, with planets that look a lot like Earth, being the right size, the right distance from their sun. I think you're going to find that there is going to be life discovered on other planets, probably within the next 20 to 30 years, I'll bet you. The odds are getting more and more in its favor all the time. 15 years ago, we used to discover exoplanets. That's what we call a planet outside of our solar system that's orbiting around another sun out there. So it's a solar system, right? That's the definition of a solar system. We used to find about one exoplanet about every 3 months. Now that we know what to look for and we've kind of developed some techniques to do it, we're finding about 30 a month. And we have identified about 20 of them that kind of fit lookalikes for Earth, and that even got them prioritized as to which ones we should look at first to see if there's life there. And to find out if there's life, first of all, you look for, is there water there? Is there carbon compounds there? Is there a heat bracket that things can maybe survive in? So those are things we can measure with spacecraft. And then you can figure, okay, these are our 2 best shots. Let's go do some detailed work there. It's going to be pretty exciting. It's going to happen. So anyway, stay tuned. Okay. So that's the solar stuff. Let's change gears here a little bit. And what does all of this solar stuff mean for the way Earth is constructed? And how do we know it? I mean, so far I've been telling a pretty good story, but the proof is just, in a lot of cases, being developed. Our picture of the beginnings of the solar system there in Orion's belt, our Hubble Space Telescope picture, man, that's pretty new evidence. That's only been there about 20 years that we've had that picture, and yet the condensation and nebula theories are both about 200 years old. So the theories have been hanging together, and the proof just keeps mounting up, and the proof that we're getting now is pretty striking. Okay, so how does this tie in to how Earth is put together? Well, remember we said that geology is kind of a big inspiration for art and all that kind of good stuff. Well, here, this is a picture of a purgatory. It was done back in the late 1700s by John Martin. And these are the fallen angels entering pandemonium. Pandemonium, as we know it today, is chaos, and essentially purgatory was thought in those terms. And this is part of, again, John Milton's Paradise Lost. This is the first one, book 1. And that was what Martin used for his ideas of this portion of mankind's future. So, well, it's always been kind of in the general picture as to how people consider heaven and hell and purgatory,